Alright, hello everybody. This is my first time I've ever made a math video, so let's see how it goes. So I'm hoping we can do this just like we would in class, but you're just going to watch this from the comfort of your own home. So we're on to a new chapter, which is chapter 6, which is all about random variables. So let's just take a little detour here. I'm a soccer coach, and let's say we wanted to know, we're going to a soccer game about how many goals are going to be scored in this game. Soccer is a pretty low scoring game. So how many goals would you expect? Well, that is an example of a random variable. It's going to be, the variable x is the number of goals someone could score, and it ranges from different values. It can take on different values for different games. So that's going to be our very first thing we're going to have in our notes, is we're going to have a random variable. So a random variable is a numerical measure of the outcome of a probability experiment. So our question here is how many goals are going to be scored in a soccer game, and that's our random variable is a number of goals scored. Now there's two types. There's a discrete random variable, which is going to be when the random variable has finite or countable numbers. So this would be an example with goals scored, because you can't score half of a goal or a third of a goal. It's you score 1 goal, 2 goals, 3 goals, 0 goals. So it's only these points here. That's a discrete random variable. Now the other kind is called continuous random variable. We saw these terms earlier, discrete and continuous. Remember, discrete, that was how many eggs does a chicken lay, versus continuous, how much milk, because it could be anywhere between 0 to whatever, but the eggs, it had to be whole number counting numbers, right? So continuous random variable, if we're thinking soccer, maybe that's how much or how many miles a soccer player runs, because they're not going to run just in increments of miles. Their distances will change, okay? And so it could be anywhere between 0 to 20 miles, right? All right, so now what we're going to go to next is what's called a probability distribution. So this provides, this is only for discrete random variables, which is mainly what we're going to focus on. The probability distribution of a discrete random variable x provides the possible values of a random variable and their corresponding probabilities. It can be given as a table, a graph of a formula. We'll see examples of that. Now here are some rules for our discrete probability distributions. Remember this symbol here? This is sigma. It means sum. If we were to add up all of the probabilities, what are they going to add up to? And it's 1. They always add up to 1. And each of the individual probabilities are between 0, which means it would never happen, and 1, which means it would always happen. All right, now our first formula here is going to be this, and it looks a little scary because it has some Greek letters in there, but it's not so bad. It's just saying the mean of our random variable x is the sum of all of our different values times the probability of those values. We're going to see how that's used quite a bit today. And so x is the value of the random variable, and p of x is a probability of that specific value happening for the random variable. So what this means is, we'll see in some examples, like with the soccer example, what if the expected number of goals was 2.3? What does that mean? Okay, well, kind of our interpretation is, as the number of repetitions of the experiment increases, the mean value of the end trials, meaning the mean of the observations, will approach mu sub x. That's our expected value, the mean of the random variable x. In other words, if we repeat the experiment many times, we expect the mean number of observations to equal the mean of the random variable. So you might go to one game and they score 0 goals, and you might go to another game and they score 6, because it will change. But as we look at many, the average of those is going to be our expected value, which is the mean of our random variable. I'm going to write in here where I said increases. So larger sample sizes are always awesome. So we like large sample sizes. Okay, so then I use the phrase expected value, and that's just another way of saying the mean of our random variable x. So expected value is another way to say that the mean of a probability distribution, what we would expect to happen in the long run as we repeat the experiment more and more times. The mean of the observation approaches this value. All right, so we've seen some vocabulary here, some definitions. Let's actually just go and do an example, okay? Okay, so let's say you guys are planning out a family and you're saying, how many kids should I have? What is the ideal number of kids in a family? I come from a family, we had 6 kids in my family, same with my wife. But we only have 3 kids. I think everyone has a different number for what is ideal for them. So basically what we have in this example was there was 900 American adults and they were asked how many kids would you consider ideal. And there's a table here, let me just zoom in a little bit so you can see that. So this adds up to 900. And this is how many children they said would represent an ideal family. Okay, now the first thing we're asked to do is to construct a discrete probability distribution. There's not a whole lot of room here. So what I'm going to do is just do this above this, okay? So what we're going to do are different values. Our random variable x is a number of children. So what were the different values we said x could be? You could have 0 children, and then you could go from 1 all the way up to 6. Now what we want to figure out is what's the probability of each of those values. 10 out of 900 people said their ideal number of children is no children. They don't want kids. So then how do we figure out that as a probability? Well, that's when we go in our calculator, we do 10 out of 900, and that gives us 0.011. Then we'll go to 1 out of 900, and that's 0.033. 2 out of 900, that was our most, or sorry, not 2 out of 900. 2 children had 520 out of 900. That was our highest. That's 0.578. 3 is 250 out of 900. That is 0.278. 4 had 70 out of 900. That's 0.078. 5 had 17 out of 900. That's 0.019. And lastly, 6 had 3 out of 900, that's 0.003. So this is our probability distribution. Now, how could we check that this is a valid probability distribution? What should all of the probabilities add up to? And it should add up to 1. The other thing is that each probability should be between 0 and 1, which it is. If you want to check that, go for it. Alright, so now the next one, I'm going to stay kind of over here for a second, but it says, construct and interpret the mean of the random variable x. Okay, this is going to go back to the formula we got on the previous page. Let me just go back to that. In order to get the mean, we are going to have to take each value our variable can take, that was 0 through 6, and times it by its associated probability. So if I were finding that, I'm going to just stay here to do the work. The mean of a random variable x. I'm going to take the value 0, and I'm going to multiply it by the probability of people choosing that, which is 0.011. And then I'm going to add that with 1 times 0.033. So we're just multiplying straight down like that, and then adding those all together. So 2 would multiply with 0.578. 3 would multiply with 0.278. is going to multiply with 0.078. 5 multiplies with 0.019. And lastly, 6 multiplies with 0.003. I'm going to put that in our calculator, and what we end up getting is 2.45. Now, one thing that throws people off is they're like, you can't have 0.45 children. Well, this is saying that if we were to look at many, many people and ask many, many people, what is your ideal family number of children, that the long-term average is going to be 2.45 children. So there we go. That is the mean of our random variable x. In other words, our expected value is 2.45. Some people try to round that and don't leave it like that. So that's how we compute and interpret the random variable. Next, we're asked to compute and interpret the standard deviation. Now, the standard deviation, there is a formula, and it's kind of tricky. So guess what we're going to do? We're just going to get your calculator and have your calculator do it for us, because it would take up a lot of space and a lot of time. So, do you remember how to make a list in your calculator? I've already gone and created my list here. So, just as a quick refresher, you go to, if you're at home, you're going to click on your list and spreadsheet, and then you've got to give it a name and probabilities, and then probability of that, and fill it in. Now, I've already done that here, and there we go. So now what I'm going to do is I'm going to come and I'm going to do the one variable stats, because we only have one variable here. If you remember, to get the one variable stats, get the info, we do the 411. So I'm going to go to Menu, Statistics, Stat Calculation, and one variable stats, Menu 411. We only have one variable, but the different values have different probabilities. I'll show you how to do that. So what we're going to do here is we are going to choose our variable child, and then the probability of each value for the child is what we're going to do in the frequency list, because they had different probabilities. So all we're changing is we're adding a frequency list here. Then I can go through and see, hey look, the average is 2.44, which is what we came up with before, rounded 2.45. So that's good news. It means we're doing this right. Now if we scroll down, we can see that our standard deviation is 0.83. Remember, standard deviation is the average distance from the mean. So although our expected value is 2.45, that can fluctuate on average by about 0.83. So that's how you calculate the mean and the standard deviation of a random variable. Alright, so now if we were to go back to our notes, so I'm going to kind of move over to here. So we computed, the mean was 2.45, and I already forgot the standard deviation, so I'm going to go back, it's 0.83, great. Okay, so then it asked me to draw a graph of the discrete probability distribution. I'm just going to use the probabilities from before. 0 was like 1%, so that's very low. 1 was 0.33. And don't worry about this being perfect, just we're trying to get an idea of what shape it's going to be. 2 is 0.578. 3 is 0.278. And then we have 0.078, and then we had less than 1%. Now I actually kind of messed up with my numbers here, so I'm going to cross those out. This was 0, that's 1, 2, 3, 4, 5, 6. Sorry about that, but there you go. So there's our graph. It looks fairly symmetric, maybe slightly skewed to the right, but it's good for us to look at those, and you'll see why in a minute here. Now, last question on here, part E says, what is the probability that a randomly selected adult family thinks that the ideal number of children is 2? Well, how many total people chose 2? And that's going to be 520. And our total number is 900. 520 on 900, that's 57.8%. So the probability of randomly selecting someone who thinks 2 is pretty darn likely. It's more than 50%, 57.8. So that's how you work with random variables, find the mean and the standard deviation. Not too shabby, right? All right, we're going to keep on going here. Now, instead of talking about soccer, we're going to talk about baseball. And we're going to talk about the number of hits a baseball player obtains in a game. So here's our chart. And this time they're not giving us the number, they're giving us a probability, so that saves us a step. And let's go through. First off, it wants us to verify that this is a legitimate probability distribution. The way to do that is look at each of those and make sure they're between 0 and 1. Check. Next is to add them up, and guess what? They add up to 1. Great. That's how we know it's a legitimate probability distribution. Now, this is going to ask for the mode. What does mode mean? It's the most repeated. So, which of the values of X, meaning the number of hits a baseball player gets per game, is the highest? And it's going to be 1. Most likely number of hits a player is going to get is 1. So then let's come down here and let's actually graph this, okay? So I'm going to come down here, graph point 166, point 33, 0.28, 0.14. Oh, that was not anywhere near where that's supposed to be. I'm sorry. 2.8's like right about there. My bad. 0.14 is actually, I think, more what I was going for, just barely, but. And then 0.03, so about 4%, and then really low percent. What shape is that? Put up your feet. Which foot does it look like? It looks like your right foot, so that is a right skewed graph. Now, in order to get the mean and the standard deviation, we're going to use our calculator. I really don't want to go by hand using 4 decimal places. Now, I've already gone through and done this for you, but you need to make sure you know how to do this on your own. You go to Menu, choose the Excel, or the spreadsheet one, it looks like Excel, and then you're going to put in hits as one variable, and then the probability of those hits. You can name them whatever you want, you just need to remember what they're for, okay? So now we're going to go through and do Menu 411. Remember, we're only doing one variable, it's just the frequency or the probability of those, each value changes, so we have to add a frequency list. So we're going to do hits and the probability of those hits, and push OK. And that's going to give us the mean is 1.63. And you'll notice here the sample standard deviation is undefined, but if you go down, the population standard deviation is there. That's what we're going to use. So our mean was 1.63. That's the expected value, or the average number of hits per game, with a standard deviation of 1.17. Now, how we interpret that is that if we were to look at many, many, many baseball players, the average of all of those is 1.63. Put that down here. But that's going to fluctuate. Our standard deviation, the average distance from the mean, is 1.17, so it could be higher, lower. Obviously, you can't get lower than 0, but that gives us an idea of what to expect in the long run. Okay, so then lastly, it says, what is the probability that a randomly selected game, a player got 5 hits? Well, if we look at how often did that happen, it was already given to us, it's 0.0244. Is that unusual? Well, what's our cutoff for unusual? What makes us think, that's not very likely? And it's 5%. Is that less than 5%? Yes, so we would say that it would be very unusual for someone to get 5 hits in a game. All right, we're doing great, rolling right along. Let's just do a couple more examples here. These are going to be a little more realistic in a real-world setting. best one to start off looking at is with what we call gambling. Yay! All right. So we're going to look at roulette. Alright, so in a game of roulette, hopefully you've seen it, that's the one where the wheel spins and they throw the metal ball in and then they can make a bet. In the game of roulette, a player can place a $5 bet on the number 17 and have a 1 in 38 probability of winning. If the metal ball lands on 17, the player wins $180. That's a lot of money for one bet. Otherwise, a casino takes the player's $5. So you get a lot of money back, but it's really not likely you're going to win. Okay? So now, what is the expected value of the game for the player? Meaning, if you're to do it many, many, many times, what's going to happen? Well, you might win occasionally, but you're going to lose a lot. So let's just look at the event. So the event is that you're going to bet on the number 17, and it lands on 17. Awesome. In that case, you won $180. So I'm going to say you gained $180. But it's really unlikely that happens. That's only 1 out of 38. Now, what's the other event? It's going to be that you don't get 17. In that case, you lose your $5 bet, and it's really likely that's going to happen. It's going to happen 37 out of 38 times. Now, what if your game plan is, I'm just going to play this a whole bunch of times? Are you going to end up out on top or end up on bottom? You're going to lose a lot, but you'll occasionally win. So how does it work out? Well, we're going to use our formula where we're just going to multiply these and add it together. So the mean of our random variable x, which is going to be how much money we're making here, is going to be, we're going to take 180 and I drew the lines going the wrong way. We're actually going to go this way. 180 times by its probability, which is 1 out of 38. Now, the other one is going to be -5, and we're going to times that by 37 out of 38. We're going to go in our calculator and plug that in. Now, when we do, it gives us -0.13. Now, that's an expected value for one game, basically. So if you played 1,000 times, how much would you expect to win or to lose? And the expected value is, the more we do this in the long run, you're going to end up with -0.13. Now, you might look at that and say, well, that's pretty darn close to 0. However, it's negative, which means what? Means the house always wins. That's the saying that they say in Las Vegas, is that the house always wins. So they're always taking in more money than you're winning, but you're winning enough that you want to keep on playing. So that expected value is going to be how much you're making over that long